We'll next turn to Chapter 18 on the log normal distribution, which we'll develop in 5 modules. This chapter is going to give us some additional insights on materials we initially developed in Chapter 11, and these insights will also provide some additional understanding of the Black-Scholes formula developed in the subsequent chapter. Before we turn to the log normal distribution, we'll do a review in our first module of the normal distribution, which should be familiar to all of you. First of all, the normal distribution's probability distribution function, or PDF, is graphed here, and we can see its functional form in the upper right-hand corner. This should be a familiar function to all of you. And mu denotes the mean of this distribution, and sigma its standard deviation. And you'll see that, of course, that as the standard deviation goes from 1 to 1.5, the distribution of this graph flattens out and gets more dispersed. And that, of course, is consistent with our understanding that the standard deviation is a measure of dispersion, and as it gets larger, one sees the probability distribution function, in fact, also flatten out. Here, the notation the author uses, it looks like a capital phi or a capital phi to some of us, and it's also often expressed as a lowercase Greek letter phi. The normal density function is symmetric about its mean, and that was certainly apparent from the graph. And if we express that mathematically, what we're saying is that the value of the probability density function, if we move x units to the left of the mean or to the right of the mean, the functional value is the same. And that's what we understand to be symmetry, and symmetric about the mean specifically. We also have standardized notation that if x is normally distributed, has a mean of mu and sigma squared, it's convenient to express it this way. X being normally distributed to capital N, and then you identify the mean and the variance. It's not uncommon in some books, and just not to be confused by this, it's important to know the convention of any given author, but sometimes you will see this expressed as x is normally distributed, and what will be expressed is the mean and the standard deviation. I think it's more common to use mean variance, but just to watch out for that as you look at other books. And of course, the so-called standard normal variable is the normal variable with a mean of 0 and a standard deviation of 1, and this is the normal distribution that we tend to think about when we see the table of normal distribution values at the back of a typical probability and statistics book. Associated with any probability distribution function, PDF, is a cumulative distribution function. The PDF is sometimes called the probability distribution function, or more accurately, the probability density function. Here we're now looking at the cumulative function, or the cumulative distribution function. And what this does is identify the probability that the random variable is less than or equal to a given value. And so N of A is the author's notation for the probability that the random variable is less than or equal to A. And for a continuous probability function like the normal, it doesn't really matter whether we put the equality in there or not, that this would be, of course, the same as the probability that Z is less than A. I think this is the correct definition of a cumulative distribution function, that it's the probability that the random variable is less than or equal to But in some applications for the normal, you'll see a less than, but not to be confused, they are the same thing because the normal is continuous. If you're working with a discrete or a mixed probability function, you have to be careful, and you must include the equality in the density, in the distribution function definition. And of course, for the normal, it's simply the integral from minus infinity to the value a of the probability density function. And these are precisely the values that one sees in tables, although I should correct that. More commonly, what you see in probability tables is the value, probability table. They actually give you the integral from 0 to a for various positive values of a, with the understanding that you simply need to add 1/2. Some tables will give you the integral from minus infinity, but obviously if you just integrate from 0 to positive a and add the number 1/2 to the probability value, you get the normal distribution function.